Okay, we're going to solve some problems involving two different systems that we must compare. Here's the first one. A first mass spring system composed of a mass m and spring constant k is oscillating with a period of 6 seconds, t1. So here's the first system. The mass of the spring is m. We've used sort of some shorthand here, but the spring constant of the spring is k. And the period of this whole thing is t1 equals 6.00. And then we've got some second different system down here. And what do we know? Well, what's the oscillatory period? Okay, find its oscillatory period. For a second system composed of a mass 45 m, so we can see it's a bigger mass, and a spring constant 9/5 k. So it's a bigger spring constant, it's stiffer, and we can see that in the picture. You know, it's a thicker spring, so stiffer. Okay, how do we solve? Well, let's use the equation for period of a mass spring system. And these are both cases of simple harmonic motion. It's frictionless, we don't say that, but it'll say that in the problems you solve. So we'll add that it's frictionless to simple harmonic motion. We've got 2 pi radical m over k. And this m refers to the m that they gave me. This k refers to this k I was given. Alright, so how about down here? What's t2? Oh, that's t1. And let's see, I know that it's equal to 6. t2, okay, 2 pi square root of mass over spring constant. But I can't just write down m here, because the m, remember, is the mass on top. It's a smaller mass. This one down below has a bigger mass of 45 m. So let me type right in 45 m. And what's the spring constant for the one down below? It's 9/5 of the original k. Alright. First thing I'm going to do is get rid of this fraction in the denominator. When you divide by 9/5 k, that's the same as multiplying by the reciprocal. So I can write this as 2 pi, take the 45 and in the 45m, instead of dividing by 9/5 k, I'm going to multiply by the reciprocal, 5 over 9k. And what do I have? Well, let's see. This and that simplify to 5. So 45 over 9 is 5. And what do I now have under the radical? I have 2 pi. I'm going to put the m over k together. And then also under the radical, I have 5 times 5, which is 5 squared, or 25. Maybe I'll write 25. And what can I do next? Well, why did I separate out the m over k? Why did I separate that out? Because now 2 pi times the square root of the original mass over the original stiffness, this whole expression equals 6. How do I know? Because I have an identical expression right here. 2, I've got a 2, I've got a 2, I've got a pi, I've got a pi, I've got radical original mass m over the original spring constant k. So this whole thing is 6, and I can substitute in. Alright, and when I substitute, what do I have? t2 is this whole thing, 2 pi radical m over k, is 6 times, what's square root of 25? That's 5. And so t2 is 30 seconds. Now notice, it would be wrong for me to ignore the radical m over k. If I write this step in the following way, here's what I might have done wrong. I'm going to show you something that's wrong. It would be incorrect to write, you know, square root of 25 like that. Why is this wrong? Because I'm leaving off the 2 pi. I'm leaving off the radical m over k. So you can't just focus on the numbers alone and leave everything else out. You have to include the 2 pi radical m over k. You just make that separate from the coefficient. Okay, let's try another one. A first simple pendulum of length L is oscillating with a period of t1 equals 14 seconds on planet X, where g is g. The acceleration due to gravity is g. What's the oscillatory period of a second simple pendulum of length 1/18 L? Oh, look, see how small it is compared to the first one? On planet Z, where the acceleration due to gravity is 2g. All right, well, let's work it out. Okay. So the length of this pendulum from the center of the mass of the ball up to the top, to the pivot, that is L. And the value of g is just g. Okay. And the length of this guy is way shorter. Its length is 1/18 L. 1/18 of this length. And the g is stronger, so it's 2g. Okay. Let me write the equation. The equation for period of a simple pendulum is 2 pi radical L over g. And when I plug in the L, that stands for this L. When I write the g, that's this g. So the t here is the period of this guy in blue. What's that period value? It's t1, which equals 14 seconds. 14. Right there. So what's T2 then? Because that's what we're asked to find, the oscillatory period of this one, of the second system. So T2, same thing, I do 2 times pi, radical length over g. Now it would be wrong for me to put an L and a g here, because the second does not have the same length L. It is much smaller. Its length is only 1/18 of the original length L. And the g value is stronger, so I can't just put g, because that would imply that this was equal to this, which is wrong. So instead I have to put the 2g. That's the acceleration due to gravity on planet Z. Okay, so what do I have to do? I know I'm going to have to get the 2 pi, the radical L, the radical g, all together in one group, so that I could next substitute in, for 2 pi radical L over g, substitute in the 14. So let me see if I can separate or put those together. Okay. T2 is 2 pi times, what can I write down? Well, there's a big giant radical. I've got 1/18. I'm dividing by 2, which is the same as multiplying by the reciprocal. Am I done? No, I'm not done. I've got L and g still under the radical as well. So here's what I can do now. I can break up the radical, distribute the radical to this and also to this. This is legal mathematically. So I'm going to put the radical L over g first times the radical 1 over, well, 18 times 2 is 36. All right, and now I'm almost done. I can look and say, hey, wait a second, 2 pi radical original length over original g, that is identical to this expression, which equals 14. So this thing is 14. 14 seconds. What's 1 over 36 square rooted? Well, radical 36 is 6, so this is 1/6. So what's my answer? 14 over 6. I can divide numerator and denominator by 2, and I get 7 over 3. And 6/3 is 2, right? And an extra third to make 7/3 gives me 0.3. So that's the answer.